Hi guys, let's take a look at one of our controllers that we use for hydronics, and that happens to be a boiler controller, and I'm going to specifically just discuss this related to an Aquastat relay, and specifically what it does, what their capabilities of this particular controller would be, and exactly how it kind of works and what it does in there. So you'll notice up on the top here that there are a few different models. So, and I'm going to use the Honeywell one as the example. There's certainly other manufacturers, but I'm going to use this one. So the L8148, and there's an A, there's an E, and there's a J model that are pretty common in here. And I'm specifically using the product data for this one. So there's a few things that I'll kind of go through on this. So the first thing I'll hit up on is this particular device is a you can either get it in a horizontal mounted type system, or you can even get it as a vertical type of a system as well. This particular Aquastat that we're looking at, what we call an Aquastat relay, this is a type that's going to be mounted on usually on a boiler system where there would be a well, a temperature well, that would kind of create that isolated barrier between the Aquastat sensing bulb and the fluid from the system. So it makes it easier for changeout. And we'll take a look at that coming up in a little bit. So exactly what an Aquastat relay is I always think of the Aquastat as the controlling device for the boiler. It's really a limiter, and in a lot of cases, so we kind of call it as a way to allow the boiler to warm up to a specific high limit temp. So that's part of its feature. And then there's also relays that can be in some of these as well, especially an Aquastat relay. They will include a relay that allows you to switch and control the burner as well as the circulator that's on there. So I want to hit up on some of these specifically as far as feature-wise that are important to recognize. The first thing that I'm going to deal with, I'm going to switch this over to the highlighter. And so the first thing I want to hit up is all of these model of Aquastats are all designed to work generally with a 24 volt, what they're saying is 24 volt thermostat. And I'll get more into this one a little bit later, is what we specifically mean by that. Now, most of the applications, we really don't wire a thermostat directly to the Aquastat. So it's a little bit of a confusing statement that's in there. All models are used with a 24 volt thermostat. I think simply, and we'll look at that, but they simply mean that they have a power supply that allows you to work with a 24 volt system. So some of the models, they've got specific types of terminals that might even also include you to have a remote, what they call a low limit temperature control. Now, oftentimes this low limit temperature control that we're describing, that I'm going to describe here, is oftentimes a limiting temperature control that would prevent the circulator from actually operating in the event that boiler water was not up to temperature. And the primary purpose of that is that should you have a demand for heat, it doesn't constantly bring cold water into that boiler and put that boiler into an extended period where you would be condensing. You would have condensing constantly in that boiler. So I would say this is really more of a, let's call it a pump control as a feature, as a function. So I remember some of the earlier Aquastats that I dealt with that didn't include the relays. They actually had a separate high limit and a separate low limit built into the same unit, and then you had to wire it up using relays to make these work. So additionally, let's take a look at the model that is an L8148 E and J. They've got the terminals that basically allow you to have a zone valve control system wiring on there. There's some that don't, some that do. The E model, they also you can also have it available so you can plug in a vent damper. Now, some of these boilers that are let's say natural draft, category 1 natural draft. So I'm talking about your typical cast iron boiler. They may have an actual vent damper that will close when your heating demand is done. And so that's kind of one way, or if the boiler is no longer operating, they'll do that. So all of these devices, they've got a transformer. They provide power to that low voltage circuit, and we'll talk about how they do that and what it does. And then we may this is the big thing right here. Different models will provide switching of the line, the low, or even what they call millivoltage burner circuits. So you have to kind of know what you're looking at. And as I had mentioned earlier, they come in either horizontal as well as a vertical position or mounting position. So we'll take a look further into there and proceed. All right. So in this particular handout, there's a couple of things that I'd like to look at here specifically. One of them is that I like to kind of take a look at some of the specs on these things just to see what we are dealing with here. So a couple of little things on here that we'll hit up on here is one of them is the temperature range, or what I'm going to call what they're saying is the scale range. The scale range is 140 to 240. Now specifically, I'm going to hit up on why the 140. What's the significance of 140? And what you probably will recognize or remember is that the approximate temperature of where natural gas or propane or oil will condense at is in that vicinity of around 130 degrees on typically 125, 130-ish. So what that means then is if you're going to maintain 140 in your boiler, you're going to keep that boiler out of what I would call a condensing situation, and that's something you have to be aware of. So that's a big one on there. So let's take a look at some of the other details. So one of the other things that would be relatively important to look at, one of them is going to be the electrical ampacities of the circulator circuit. So a lot of these Aquastat relays, they have the ability to control the circulator or at least provide power from switch from the main power through the Aquastat relay to allow you to energize a circulator that would be in conjunction with the boiler. And we'll look at that circuit and identify how that works. The full load ampacity, the full load circuit on a 120 volt system is going to be 7.4 amps, and they're calling a locked rotor circuit that would be 44.4 amps is how they're doing this. So if you have a 240 circuit, as you can tell, they're cutting that roughly in half is how they're doing that. Voltage and frequency. So most of the applications you guys are going to probably run into will be more likely the 120 volt circuit and 60 hertz. So now you might be saying, well, why are they listing 240 volts on here? So why they're doing that is they likely have the ability to use a secondary circuit to allow you to feed 240 volts to that circuit, to the circulator circuit. So there again, that's an unusual application. Most people are not going to have that. The line voltage for the burner circuit, that's another important one here. They're identifying line voltage rating same as the circulator circuit above. Now here's why I want to specifically bring that into your attention. A lot of times the line voltage for the burner control circuit, if you're running let's say you have a fan assisted boiler. So you might have a cast iron boiler that has an inducer fan. What they will oftentimes do is have the burner circuit actually energize the inducer motor and get that running, and then once the pressure switch makes, then the pressure switch would actually be the controlling circuit to allow the burner circuit to energize, let's say, the ignition module and things like that. So they do have some alternatives there, and again, you have to kind of watch that. That's normally the case. So a lot of times, a lot of people will have, they might put in an extra or an additional, maybe a relay or a circulator relay or a burner circuit relay that will be auxiliary to this. So, and what they're not telling us in here is specifically, but we'll see it later, is there's a completely separate circuit pole for the burner circuit as well as the circulator. And so in other words, what I'm getting at is there's a completely separate set of relay contacts that are going to be for the burner circuit as well as the circulator. So this one here might be the burner, this one might be the circulator, and so my point in telling you that is that the ampacities would logically be the same in a lot of these cases to provide you the operation of that. So anyways, that's a little bit on that. The low voltage circuit, they're listing as 0.8 amps maximum. So this actually will be fairly important to recognize 0.8 amps max, because that might be what they're using to power some auxiliary type of relays. And that might be, so for example, that could be zone valves as an example. So we're very limited on the number of zone valves we can actually use on some of these, depending on the model of the unit. The millivoltage, this would be typically your power pile stuff. So so most of the time when we start looking at this thing, your power pile is that's your 750 millivolt type of a boiler control system. So they might actually have some of those types of things out there, and it works pretty nice. It's not too terribly bad. All right, the approvals, that is fine. I'm not worried about that. If that's something you have to meet, then you can you have to verify that yourself. So the immersion well. So along with these Aquastats, they will allow you or bring to you a what they call kind of a brass insert, what they're calling an immersion well. And typically it's either going to be a 1/2 inch or it's going to be a 3/4 inch pipe thread that would be into there. Now this is not something that you normally should ever have to change. So typically that's going to be just, you know, completely part of the boiler system. So if you have an Aquastat that goes bad, what you're likely going to just do is change the Aquastat, and you can use the existing well that would be in there. The insertion or the depth that they're identifying as 1.5 to 3 inches is it's really kind of what they're inserting it into the system. All right. Let's see, max pressure. I don't ever think that's ever going to come into play. 255 psi, I don't see that as ever dealing. The max bulb temp, 40 degrees higher than the set point. So they're saying up to 265 degrees. There again, I really don't think you're ever going to run into that. But I guess where that could become a problem would be, you know, if somebody were to actually, I don't know why anybody would do that, but if somebody were to take a torch and heat that immersion well up, or the bulb, the sensing bulb up, I could see where that could be a problem. But again, very rare that would ever be an issue. This maximum ambient temp. All right, so the only thing that I could think of where, you know, let's say if you're in a boiler room and you've got a boiler mechanical room. So they're identifying a temperature, a maximum ambient temperature of 150 degrees with a 1.2 amp load on the 24 volt side, or 77 degrees with a 1.4 amp load on here. So what they're doing, or what they're really telling you, is that the higher the amps, and this is true of actually wire, this is true of relays, of almost all components. The higher the ambient, it allows you to use, I would say, or utilize less current, available current. And what they're worried about is if you have let's say a mechanical room or a boiler that is emitting so much heat out to that Aquastat, what you're doing is you potentially could burn out the transformer. And that's the concern of why they are identifying that. Again, rarely does that become a problem, but it is something that you have to be aware of. I've been in commercial jobs where the mechanical room was, you know, 120 degrees in there at times, and that gets very challenging for a lot of those things. So let's move on. All right. So I think this little table 2 is a good one to hit up on, and we'll look at specifically, you know, what I find helpful is let's say if I particularly have a an Aquastat, and one of my Aquastats here is the L8148A model. And I'm going to find that on the actual unit, or it'll be usually stamped on the cover or something like that on the insides, usually is where you'll find this. So now what I want to know is, when I see the model, is that, all right, what do we have for a burner circuit? So the burner circuit on that L8148A is an actual line voltage burner circuit. It would be mounted horizontally as far as that goes. So that means that you would have, you know, and primarily in this example, it would be the Honeywell logo would be in the horizontal position. It's the only way you can turn that Aquastat to have it look decent. This is typically something you would see used on an oil-fired boiler, is the L8148A. That's a very, very common Aquastat relay. It does obviously provide the provisions for what we talked about earlier was a low limit, and all of these will allow you to do that. All of these will. The high limit, absolutely. That's the whole purpose of the Aquastat relay, is the Aquastat itself is the limiting device. A second limit, none of these do a second limit. So in your bigger commercial jobs, you likely would have a different type of a limit, and where you would have another device mounted in a different well, and that could act as the secondary limit. So that's something that is very, very common with, I would say it's extremely common in commercial jobs, where we would have what we call an Aquastat high limit, and we would have the high limit on a typical boiler, and then the secondary limit could potentially even be like what we call an operating control. So that where we could actually control the boiler at varying temps, and that's another way to deal with this. The circulator control. As far as circulator control, it's saying, you know, it can be added remotely. So that could be something where you can do this, you can control this, but typically what happens is the actual relay that is on the Aquastat will actually give you a set of contacts to control this. So it's what they're telling you is can be added remotely, but it technically is dictated based on the T-stat input. So when there's a T-stat input, the T-stat input will tell that relay, hey, we need the circulator running. So that's kind of what it is. And the other thing is the circulator control. The other part of what they're talking about is even like a low limit control as well. And again, we'll look at that in a little bit. All right, max number of zone controls that can be used on here. So this is probably the one that you really need to pay attention to, because we're the ones that go out on these sites, and we'll be wiring up control valves, zone control valves. So what they're telling me is that on the line voltage burner circuit application, there is no provision whatsoever, none whatsoever, that allows you to control any type of a valve or a relay for any type of zoning. So that has to be done externally, is the way it would have to be. So this relay Aquastat, this L8148A, has no ability to power any external controls, and I think that's the thing you might want to take out of that. So that means if you've got a zone valve and you say, well, the Aquastat has a transformer, I want to just use that one, it will not work. Thermostat input required, all they're telling you is it's got to be capable of handling 24 volts. So that could be any relay or anything like that. And then, of course, what they call a manual auto switch. Some of these units have what they call a manual auto switch, which will allow you to either have it where you can manually keep the boiler temperature up all the time, or you can allow the burner circuit to cycle with a heating demand. And that's kind of what they mean by the auto manual switch on there. All right, so let's take a look at the E model. And the E model is probably, I would say, that's one of the very common Aquastat relays. And this particular one here has a low voltage burner circuit, so that would be what you would go to usually like a 24 volt input on an ignition module, if you have an electronic ignition system. The mounting case, obviously vertical, you know, that's, again, I don't worry too much about those things. All the other things I don't need to go through anymore. But here's the kicker. Over on this side, they're telling me that both of those two lower models on the bottom side here, both of those, the E and the J model, allow you to control up to 2 zone, what they're calling zone controls, which are really, they list this as item B on here. Item B is a number of V8043 zone valves. So this would be like your Honeywell zone valve, and they're saying we can power up to 2 of those valves. Any more than that, you will not be able to do that without adding additional transformers. So that's kind of what they're doing in there. I would not recommend adding any additional zone valves beyond that number, beyond 2 of those in those cases. In fact, I rarely even like to use the boiler's Aquastat internal transformer power supply to power up zone valves if I can help it. But that is something that you have to be aware of, that will do that. So that's one. Zone, you know, like say if I have a relay, they list this as item C. What they're getting at is they make a specific zoning relay or a pump relay that they're identifying, and they're identifying this as an R8230C relay, and they're saying you can power those relays with up to 4 of those relays can be powered from the transformer that's internal in the control, and that will allow you to allow that system to function with up to 4 zones that would be individual zone pump applications. And again, the same 24 volts that we had talked about earlier. So that's really a big one on here. And then if there's obviously, you know, there's some models I talked about earlier about can control a zone valve and things like that that you have to do on there. There is one other thing that I want to point out too, this item E on there. So the note E, they talk about models available with that plug, the L8148E. That is and a 50 VA transformer. They're used with these Honeywell SV9500 smart valve systems. So those smart valve control systems, you have to be a little bit careful on there that if you are going to be doing that, they're specifically telling you, you know, don't power the zone valves if you have a system that has a smart valve on there. That it would be better to not do that. And I would much rather see us use a zone valve control system, a zoning control board from a diagnostic standpoint. I think that makes the most sense. All right. All the other things we hit up on there. Now, they talk about a thermostat anticipator setting of 0.2 amps. Unless you are using one boiler, one pump, and you are circulating through all the zones at the same time, and you don't really have any individual zones, you know, and you have a thermostat that's so basic that has the anticipator, they're telling you what the anticipator should be set at approximately. It's very low. Again, most of the time with any electronic thermostats, we're actually not really doing that, but they do tell you, you know, what the scoop is on that. So, all right. So let's take a look at the specifics and terminals and how all that works. So this particular model is the L8148A model. Now, on the face of this model, I'm going to point out a couple of things. This right up here, that's the grounding screw on there. So this should be grounded to your chassis electrical ground on that system for this, and it's just purely a safety thing. They have an L1, so this would be, of course, your 120 hot in this particular case. They also identify an L2, and that would, of course, be your 120 neutral, most likely, in that case. And then there's a terminal 3 that we'll deal with. Now, on the A model, remember earlier we saw that, and I'll go back to this to point that out. So remember how it said the A model will not control any zone valves or relays. Now I'm going to show you why that is. This little tiny transformer that's identified here is just enough to literally pull this relay in, and that is it. That's all that it can do. The 2 thermostat terminals right here are doing nothing more than completing a circuit. And this would, of course, go to some either thermostat, if there's only one zone, or it would have to, or it could go to some relay contact that could complete the circuit. It's either or, one of those two. Your circulator terminals, this is basically going to be sending, again, earlier we talked about these relays that are in there, the relay contacts. One of these is going to be for the burner circuit. One of them is going to be for the circulator circuit. The circulator circuit's going to feed power to the C1 terminal directly on from this thing. So this would maybe go to C1. And this would, of course, go to B1. And we'll see the internals of this. And again, you can kind of see the skinny on here. This right here is the actual high limit control. So this is the part that the sensing bulb actually goes to on this device. All right, so before we go through the E model, let's take a look at, I want to take a look at the diagram of the A model while it's fresh in our head. So the A model, the way they're identifying this here, you might have noticed here, so we talked about the wiring in this, about the hot, whoops, talked about the L1 being the hot, L2 being the neutral, and then they have a terminal 3. So remember earlier when we talked about this low limit controller, that's what they were dealing with, was that low limit controller was a way to kind of keep that boiler, you know, up to temperature so that we're not creating a problem with the application. So let's take a look at the internals on this device. This is by far the line voltage one, like this one, is by far the simplest of all of these controls. So when we look at an application like this, when I see this, I've got L1 that's going to feed my hot. As soon as I power from the hot terminal to the neutral terminal on L2, I am powering this tiny little 20 VA, tiny little transformer. Nothing much on this system at all. Now, on that, there we go. And on the low voltage side, that 24 volts, you'll notice, is doing nothing more than energizing this 1K relay. So when there is a heating demand, and up on top here, you'll notice how they're showing you this thermostat. So any 24 volt thermostat that is handled, that's designed to work with 24 volts, is doing nothing more than completing this circuit between T and T, is really what they're trying to do. So when we complete that circuit, we are powering up, we're going to power up this 1K relay. And what's going to happen exactly when that goes on? Now, even before that relay gets energized, we're going to be feeding line voltage. We're going to be feeding line voltage directly to the 1K set of contacts, which is going to be prior to the high limit. So this B and R is actually going to be, let me mark this out here. This is actually going to be your high limit. So that's going to be the limiting device for your water temp. So whatever you set that, it should not go above that. Additionally, this device here is going to now take that line voltage with that little jumper that went to terminal 3, and that's going to go to the 1K2 set of contacts. Both 1K1 and 1K2 are actually going to be energized or let's say closed upon energization of the 1K relay. So as soon as there is this demand, this contact closure, then we're going to see a demand for the 1K of that relay. That should be energized, and both of these two relays should then, of course, close to do that. So when we look at, as I had mentioned earlier, you've got a C1 terminal. So that's really kind of going through the 1K2 relay, the second set of contacts on the relay, which is kind of going from here directly through to another set of contacts, which is now going to go to C1. That's exactly how they're identifying this and showing that here. This could be used to power some sort of a circulating pump. And of course C2, you'll see that the C2 is, yep, there we go. C2 is actually going to be your neutral. So this is my neutral. That means this is my neutral, and that means this is my neutral. And you'll notice the B2 and the C2 are actually, they're different terminals, but they're tied together internally inside the Aquastat relay. Now, let's go through. So this would, of course, be my circulator, neutral. So that would allow you to energize a pump. Now, one thing that I want to point out here in the operation of this that's worth noting, and I'll come to the burner circuit later. You will notice that immediately upon a contact closure between T and T, which could be either via a relay set of contacts that closes, or it could be through, if you had just a single thermostat, a thermostat closes and it completes the path for TNT. So essentially, whenever we jumper this out or we have a contact closure between the TNT terminals, you're really just completing this circuit from the transformer system and energizing the 1K relay. When the 1K relay gets energized, you'll also notice now that between terminal 3 to the 1K2, we are closing that, and immediately you'll notice that my circulating pump now is energized. So the point that I want to make here is that any time that there is a heating demand, the way this is wired, that circulator will always be running. And you can see how that's set. If there's a demand, this closes, you power your circulator 100% of the time. The only way that that would change is if you were to put in that low limit type of a device between on that jumper. So on your Aquastat, and I'm going to go back to the Aquastat device here, there was a jumper, and the jumper they're referring to is this one right there. That jumper. So that's the jumper that they are describing. All right. So that jumper can be removed, and that's what they're referring to. Now, circulator circuit, pretty easy, pretty well done. Let's go ahead and take a look at the other circuit. So let's talk about the burners. So now in this particular case, when there is a demand, the 1K1 sets of contacts, so it's actually the first set of contacts of the 1K relay that will close and provide power 120 volts directly to terminal B. So at this point here, I've got 120 volts. If the boiler temperature is below the high limit setting, then what will happen is this will already be closed. That relay, that set of contacts, what they're showing is, and that's going to be here between B and R. That set of contacts will close and allow you to continue the path from B to R. So you're going to be supplying 120 volts at terminal B, and you're also going to have 120 volts at terminal R. But keep in mind, that's assuming the boiler water temperature is not up to temp. If it is up to temperature, then of course that would be de-energized and you would not have power there. Of course, that from the terminal R, that goes directly through the board tracing, and that'll go directly to terminal B1. This is usually the burner circuit that would power up some sort of whether they're powering up let's say an oil-fired burner or a 120 volt transformer or something like that, that might be going to another circuit. Or I had talked about earlier about some of these boilers are power vented. A power venter could very well be powered from B1 and B2 in this situation. So it's very possible that this could be going from here directly to some sort of a power inducer motor that would power up 120 if that's an inducer motor. And then of course they might have a 24 volt transformer that is also powered up, and that would provide power to like a pressure switch and proof, like proof of flow for those systems. So that's primarily what they end up doing. But very simple system when you break it down a little bit. And at least by having this diagram, it really helps to make diagnoses to figure out, hey, this is what it's doing. It's pulling in the relay, or it's not energizing the circulator. You can then diagnose it and figure out what's wrong with it. It's a very simple system. All right, so what about externally and how might this look? All right, so what I wanted to show you is on this figure 6, what they're doing is they're showing me an oil-fired boiler system with 3 zone pumps. And how they're doing this is, in this particular application, this is one way to do it. My preference would be certainly to use a zoning board that would have maybe a 3-zone system where it would integrate all of these into one. That would be my preference. But in this case, they're not showing that. So let's take a look at this. So in this example, they're taking the line 1 and they're doing it to the L1. They're taking line 2 and they're feeding L2 in this example. So this is powering up the Aquastat relay, which is the L8148A. We also are powering up terminal 1, terminal 3, terminal 1 and 3 on every one of these relays. Now, terminal 1 and terminal 1 in this particular case is really on these R845 relay zoning, they're like an individual zone pump controller. What they're doing is they're powering up a transformer, which is why that's how this is able to function. So that's the function of that. Terminal 3 is actually going to a set of relay contacts. So for example, this would then go to, I'm going to draw it this way. That's going to go to a normally open set of contacts. And then this will go to, usually this will end up going to some sort of like a normally closed set of contacts or something like that, that they can do that. So that's kind of the way they're doing that. So this one is 3 and 4 is primarily from that manner that it's controlling to get the pump circuit. So in any one of these cases, anytime you're dealing with these types of relay systems, you want to really look at their diagram specifically on there. As you can tell in this diagram, they really don't give you a lot of information. You have to figure it out on your own. So let's take a look at specifically how they're doing the rest of this. So we know that when there is when we power up the Aquastat, we're powering up that little mini transformer. And then what we're doing is that provides us power at TNT. Now, you'll notice that there really isn't a thermostat that's actually going to TNT, even though that it says thermostat input, 24-volt thermostat input. That does not happen in most zoning panels, and it doesn't happen in most hydronic systems. So what happens then is this little zoning relay, this pump relay, will take a 24-volt thermostat. It will allow you to have a contact closure. So this is I'm gonna draw this way. So on a fall in temp of this T87F is what they're showing, but this could be any thermostat. You could do it as, with some sort of a battery-powered thermostat for that. Any contact closure, what they're gonna do is allow you to send power, and essentially you're powering up the internal relays in this system. So it's allowing you to power this relay, and they're also allowing you to power up another set of contacts in here that I'm gonna draw in here. And this other set of contacts is gonna be this. So they're gonna show this one as another isolated set of contacts, totally separate. And in this case, that's going to be this right here. You guys will recognize this here is going to act as the thermostat input to the Aquastat. is what it's going to do, Aquastat. Okay, that's what it's going to do. So let's look at how this happens. So let's say this first one has a heating demand. So this one says we want heat. Yes, I want heat. This closes, we complete that circuit. So now when that closes, that means this will close, that means this will close simultaneously. When that happens, between T, I'm going to switch that to the highlighter, between the T, this one here and this one, it'll go through here, through the contacts, it'll come back out on here, and it'll complete this set of, it'll complete the T to T circuit. Now you might remember up in the very beginning when we looked at this one, when you completed the T and T circuit, all you were doing was taking care of this relay. You were basically completing the circuit on there. So that's just something to be aware of. And electrically, we saw that up in the, we saw that in this diagram right here, where when we close the TNT circuit, that was energizing the 1K relay, closes this, and it says, okay, let's let the Aquastat do its thing. And that's really how that is, it's kind of functioning. Now, let's say we have another one of these that maybe has a demand. So let's say this one now calls for heat. So at this point, when the first one was running, the circulator was energized. But remember, oftentimes on these, we don't even power anything on these on C1 and C2, because in a zoning pump application, this is going to control your pump, and this one is going to control this pump, and this relay is going to control this pump. So the burner or the Aquastat circuit isn't really doing anything other than it's just there. It's available if you wanted to use it, but it's not doing anything. Now the burner circuit, B1 and B2, B1 is going to provide, as we saw earlier, that's going to provide my line voltage into an oil burner, and the B2 is nothing more than your neutral. And you'll notice that they tied that into the white wire, which was also going to a burner or ignition control or something like that. This is the what they call in oil systems. This one's your primary control. That's what that is. So that's actually going to be what I'm going to call my primary control. On that primary control, you've got a CAD cell, which is really a light sensor to detect a flame. And that's really, the way those work is if I energize B1 and B2 and I say, hey, I want this burner to run, assuming the burner lit off, this will see light and it'll give you a very low resistance to kind of complete the path for F and F. And when that's low resistance, that'll allow the heating or the safety circuit to be eliminated or removed from stopping the burner from running if there is a problem. So that's the kind of the thing that it does on here to some extent. So we certainly would not, we certainly wouldn't jumper this out unless we were trying to do some field diagnosis, but typically that's how that works. So anyways, a very simple system. So let's take a look at the next one. So this one we have a heating demand, and this one we'll say we have a heating demand. So either one of these things, let's say that we want to do some sort of control. So now this has got a path that's completed. We now take our power and we go from this circuit down to here, and we power this one up. This one is another set of isolated contacts. Now you might hear me talking about isolated sets of contacts. It's imperative that those are isolated because you certainly can't confuse the 120 volt circuit from the burner circuit, and between 5 and 6 is how you'd have to do that. So you have to really watch that. So because this, I'm going to just label these here, and this one here is, this one's going to be number 1, I'll say. This one's number 2, and this one's number 3. If any one of those, 1, 2, or 3 call, we complete the circuit here. If it's zone 1 or zone 2, they're both making a contact closure, and as far as boiler and the Aquastat's concerned, it's completed the circuit and the system should have a demand. So how do I use this to my advantage? So if any one of these burners or boilers or these pumps are energized or being told to operate, it's going to take a heating demand, it's going to take a contact closure that's going to allow the or the pump circuits to run, and it's also going to complete the circuit. So if I walk up to a boiler in the field and I take my meter out and I check between the T and T terminals, if there is a demand, I am fully expecting to see 0 volts on those T and T terminals if there is a demand. It would be no different than if I took a jumper wire and I jumped it from T to T. Your meter would be measuring a potential difference, and of course if there's a jumper on there, there is no potential difference. So that's kind of one of those that functions there. So that's kind of one of those where in the field, if you run into this, you are going to need to do this. If you're trying to figure out, hey, I think I might have a bad set of contacts, or I have a bad relay, or a bad zoning board, or a bad R8045A for the zone 3, or whatever it might be, you're going to have to individually test those out. You're going to have to go to zone 1 and let's see what happens. And let's go and measure that out. And zone 2, and we'll de-energize zone 1 and then go back to zone 2 and energize that one. So you'll have to do them individually without a zoning board. The beauty of a lot of these types of relay systems is many of them do have like LED lights that are on these things. So you might have an LED that says, hey, I'm powered, and you might have another LED that said, hey, by the way, we have a T-stat demand or a heating demand. That makes it a little bit easier on there. So that's a little bit of the operation and the of kind of how the L8148A functions in a line voltage application. Okay, so let's take a look at another Aquastat, and that's the L8148, the AE, or the E and the J model. That is a different one on here. So what's different? How does it work? So this is what we're gonna focus on this one. This particular model, you'll notice, has some varying terminals, and you're seeing it, of course, here. I'm going to show it to you what it's going to look like when you're seeing it, when you're staring at it right in front of you. It's going to look like this one. And what this one is going to show me, you'll notice that between this one, little tiny transformer on the top, and this one, now you actually have a much larger transformer that allows you some additional functions. You have some thermostat demand terminals. You have some thermostat demand terminals between TV, T. You have those. You have still have your burner circuit terminals. You have line voltage, L1 and L2, C1 and C2. A lot of it looks very similar. The big change is really up here. It's in this area. That's probably your biggest change. So let's look at the specifics on maybe how that is going to work. All right, so when we look at this diagram here, what is going to happen here is, let's look at the nitty-gritty details on this one. So when we look at the individual diagram of what's going in internally, this is really gold in here. So this is what you want to really be looking at, is this diagram. Of course, my 120 hot, my neutral, that goes into here, 120. This is where I'm powering my transformer. But what you have in this one that you did not have in the other ones is that now I have the ability to actually power other things from this transformer, because now I have a spot where I can go in and get a dedicated common from the 24 volt side, whereas before I never had that ability to do that. So that's one advantage. So I can actually get between terminal Z and between terminal TV, I can actually verify that transformer by measuring 24 volts whether there's a heating demand or not. I can always get 24 volts on there, and that's assuming that I've got my 120 volts hot and my neutral, obviously, to this device. So all the time that is. Potentially, if the Z to W jumper is in here, then you'll also have it on terminal W is where you'll have that as well. So, and that's usually a jumper that either is factory installed or you have to install it. All right. So what else is going on in here? You can, you'll notice on here as, let's say if there's a demand or a thermostat demand, and I'm going to go to this diagram here, you'll see how they are identifying this, that 24 volt thermostat that we had talked about earlier. They're now using terminals TV and T. This may be an actual thermostat, heating thermostat, or it potentially even could be just a set of relay contacts that is completely isolated that goes between your TV and your T. That's how they're going to do this. So now when I go to this diagram, I can see how if there is a demand on TV and T, we are actually completing the circuit of the 1K type relay. That 1K relay will become energized. That will close the 1K2. It'll close the 1K1. This one here, you'll notice the 1K1 in this diagram, I'm going to go to the highlighter. This 1K1 in this diagram is now going from the 120 hot through the 1K1 relay to power the circulator pump. So what that tells me is that any time that there is a heating demand, I will definitely get 120 to power up some sort of a circulator motor, a pump, we'll call it. And C2, of course, is your neutral. Now, what is different between the previous model and this one, in addition to this, is you'll notice that the B1 is now going to be your 24 volts. So this is now going to be powering 24 volts on the B1, and that's, most likely going to be either 24 volts hot or the common, depending on which one you are using, or and a lot of these aren't really grounded, so it's really it really becomes a little bit challenging to some extent, because if you actually took and put a jumper, or let's say went from terminal Z to the chassis ground, you could actually ground that individual transformer. Generally, I never see this ever done in the field. So my point in telling you that is that if I went from the chassis ground to Z or to T or to TV, it's a floating voltage. It's not tied together anywhere, which would basically give you these kind of bogus numbers. No matter what side you check it on, you may be getting 24, 26, 28 volts. You might be picking that up. So that's just something to note from a diagnostic standpoint. This B1 is 24 volts, and we'll call it maybe our 24 volts hot, and the B2 will consider that as my let's call it my ground or my neutral. Typically, I usually figure this one as my hot, and I usually figure this one as my 24 volts common, is the way I usually set this up, and most people will do it that way as well. And that's on the secondary side. So the interesting thing about this is if you look at between terminal TV right here and terminal B2, you can kind of tell they're actually tied together electrically. So that's, again, why when you are looking at these voltages, and I have a heating demand here, I'm just kind of basically completing the path for TV to T. And then that's going to allow 1K to run, and away I go. And that's generally how this will work. So let's look at the specifics of there. So enough of that. How does this look like with a zone valve system? Well, You could certainly have used a zone valve system with the other type of application, with the A model, but your wiring would have been slightly different. So in this example, you certainly would have had to have some sort of an electric, some sort of a transformer that would have allowed you to power up 24-volt devices, assuming you're using a 24-volt actuator. So the Aquastat now, what we have to find out is they're going to utilize this on these zone valves. So for this Aquastat is going to look for a heating demand, not from a thermostat, but what will happen is the thermostat will actually power up the zone valve actuator. And when the zone valve actuator gets powered up, it's going to power up a little motor inside those little zone valves. Now, in a zone valve, the way they work is you're going to have a little zone valve synchronous motor, and then you're going to have, typically we'll see this, is there will be a completely isolated set of contacts. So when they're talking about, in this device, this thing that's called an end switch, what they're getting at here is that is this little completely isolated set of contacts. So what that's doing is completing the path for when that motor drives that actuator fully open. At that point does this close, and when that happens, now we will simply complete the circulator path between the circuit path for T and TV. That's how we get the demand. So on any type of a zoning system, if we ever had a question, we're like, gee whiz, and I don't know if my thermostat called this zone valve open, the first thing you'd really want to be checking is the zone valve actually energized, and is it actually opening the zone valve? Usually a lot of our residential zone valves, they can be normally closed or normally open, but most of them are going to be normally closed, and you power them to open them up. And the way you'll notice this, they're also completely isolating. Every one of these zone valves has a separate set of contacts that are going to be in parallel, that are isolated, that will allow you to energize your T and TV to provide that path. Anything more than 2, you definitely have to put the Aquastat, the extra transformer, in here to power that system. You'll also notice that, and this is important to recognize, there under no circumstances do you ever want to power up, do you want to kind of, or let's say, interfere or interconnect transformers? Be very careful with this. If you're going to have this transformer that is on here, that's shown in this case, I would highly recommend powering up, getting a transformer big enough to power all of the zone valves and not use the internal transformer in the Aquastat. It's more from a diagnostic and a fail-safe type application. I've seen these applications where guys have installed these in the field, and this transformer was fighting against the transformer that was internal in this system, and that created a problem. So I generally try to isolate those and do them differently, so that I'm not using both of these two. I'm not using the transformer here, and I'm using a separate one here, and I'm trying to tie them together. That's really kind of dangerous to do. I would highly recommend not doing that. It also would, like I said, it makes it a lot easier to troubleshoot these. So there again, if I want to, let's say we want to question, hey, I don't know if there's a demand. So first thing I had said, power up the zone valve. Is it open? If it's not completely 100% open, this little end switch will not completely close that set of contacts. That will become a problem. That will then also mean that when I take my meter and electrically, when I go from this terminal on TV and I go to T and I look at my electric meter, what will happen is the electric meter will read 28 volts or 24 volts or something like that, telling me, hey, you don't have a demand. And it's kind of like measuring the voltage across an open set of contacts. Just like I said, these are all things that you guys should know about already. So, a couple of takeaways from this. one of them that I hope you have taken away is that on all of these systems, really, the Aquastat is a temperature limiting device. The Aquastat has relays. Aquastat relay generally can have relays built in that will also control the circulator in addition to the burner circuit. When you have zone valves, typically you'll have thermostats that will power up the individual zone valves, and then you will take isolated sets of contacts to complete the thermostat demand. And I point that out simply because every one of the Aquastats in the field is going to show you and say 24-volt thermostat. And if you're not familiar with hydronic systems, you might think like I have to bring the thermostat from all the zones directly to all of from each thermostat directly to the Aquastat. That's not what they are intending to do. So electrically, we're just saying we need isolated sets of contacts. And obviously you cannot parallel three. You can't do the zone 1, zone 2, and zone 3 parallel. If you did that, anytime you'd have one of those call, you'd have thermostat 1, zone valve 1, zone valve 2, and zone valve 3. You'd have all of those calling at the same time, and that's certainly not going to happen. So that's a little bit on that. All right. And there's a few other diagrams in here. I won't go through all of them, but it's very, like I said, electrically. The only variation on here that I could share with you, and I'll have you guys expand on this if you want to read further into this, is on a lot of the more efficient systems where there is where you would have let's say a vent damper that would be on a category 1 type boiler. What would happen then is the vent damper would be powered from the respective model of device that would allow you to, it would say, I absolutely 100% I have to power the vent damper and open this up 100% prior to ever allowing a burner to run. It has to open 100% before the burner will be allowed to run, before burner operation. And so this is more typical of a lot of those systems. Now, if you are natural draft, if you are using an induced draft type boiler, then you will not have a vent damper at all. And again, very similar, but thing you have to recognize, you have to be able to isolate is the problem. When you're diagnosing systems, you have to isolate parts and pieces. Is the Aquastat doing its job? Is the vent damper doing its job? Am I getting the correct inputs into the Aquastat? You have to look at those things to go through the diagnosis for that. All right. So that is a little bit on that. The last thing that I want to get into that I think is imperative that we talk about is this. I want to show you the well. This particular insertion well, oftentimes, and you need to see this. So what happens, this insertion well is going to have an immersion well, kind of a clamp screw that's shown right here. And it'll also have a set screw. Now, what I mean by that is this little immersion well clamping screw is going to be a part that will, you have to not loosen this one up. If you do loosen that one up, you can only pull it out a little ways, otherwise you're going to break the capillary tube that's going into the Aquastat device that they're identifying here. So you want to be very careful on that. The other thing that's going on in here is this set screw that you see right here. That set screw, when this becomes loosened on there, that little set screw will allow you to pull the entire sensing bulb out of the well, and it'll allow you to actually back out that whole thing out and allow you to actually replace the Aquastat in its entirety. The well, you shouldn't have to take that out. Part of the reason for having a well is that you don't want to have to take that out if you can help it. They also are talking about in this particular sensing well using a heat conductive compound. This is very important from the sake of you want to, you know, they're showing you in this picture how they want to see contact up on top. They want to see contact down here. They are trying to intentionally do that because they want to make sure that it's not floating in air. And if you put this heat conductive compound in there, that will allow you to, it really reduces the necessity to try to make sure you have that Aquastat bent and moved up into this position in the way they're showing it here. This is a little bit challenging, but there again, be careful with this. I wanted you guys to see this because my concern is that if you go onto one of these and you have a defective Aquastat and you got to replace it, I've seen guys in the field where they have taken these Aquastats and they've loosened this screw, this little immersion well clamping screw, and they started to twist out the Aquastat. And what all they were doing was really breaking this little capillary tube, and then they still ended up having to take that out. Now, if the well or if the Aquastat is defective, I guess then it's nothing to worry about. You're replacing it anyways. But just so you know that that's kind of the process of how they do that. But that's a little bit of kind of the basics of what we call an Aquastat relay. So hopefully that shed a little light. In your textbook under modern hydronic heating, they go through a section on the Aquastat. It shows some of the breakdown of various different types of Aquastats. I would strongly encourage you guys to look at that.